All right. So now we're actually going to talk about continuous charge distributions, which is the case of not just isolated point charges, but charged objects that we're going to break up into different charge segments and find the field and potential generated by those distributions. So to begin, we'll start from the fact that when dealing with finitely many charges, we just use summation to find the net contribution. So we sum up our kq over r squared contributions or our kq over r, depending on what we're looking for. Of course, respecting vector properties for the E field. But if instead we have like a line of charge or a ring, anything that is just a continuous object, we have to model it as a collection of all these smaller charges put together. And anytime you start breaking things into really small segments and adding them back up, well, that's where the integral is helpful. So notice this is just summation of kq over r squared and kq over r again. It's just we have to add up all of these tiny segments dq. So in order to do that, the first thing we'll introduce more formally is our three types of charge density. So if you have a one-dimensional object like a ring or an arc or a line of charge, we define this lambda as the charge per length. So if you want to find the total charge, you can just integrate all of those charge per length times length segments. And there's a special case where if you're on some sort of an arc, you have to expand this dl. So we'll see that in a lot of cases, we actually have to expand this differential, where if you're on an arc, to actually expand that length of the arc out, we replace it with r d theta because there's an arc length relationship there that relates how long an arc is to what angle it subtends. For area, if you have a two-dimensional object, you can add up all of the charge per area times area segments. And the most common case we'll see of this are things with circular symmetry. So we can break up that dA, that area segment, into 2 pi r dr, because you can have any small area contribution. It's going to be a small circular ring with some thickness. So it has a circumference and a thickness. And then a similar story for the spherical case or the 3D case of volume charge density, where you have a charge per volume. And we have actually two variants of this, where if you have a sphere, you expand the volume as a bunch of spherical shells, because these spherical shells have an area and a thickness, or you do the same thing with cylindrical shells with an area and a thickness to create that tiny volume. So we're going to verify some of these properties real quick. So first of all, we want to verify each of these substitutions. So we want to first verify that a length segment on an arc can be written as r d theta. So if we think about any sort of a circle, that's circular enough. We'll draw ourselves an arc. So let's say there's something like that. Oh, that's totally not the center. Maybe something like this works better. So let's say I want to find this sort of length that's on this wedge. And this is a formula from geometry that if we know the wedge angle right here, this theta, the arc length formula tells us that this length L is just equal to the circle's radius, R, times theta. And again, it's easy to check this because we know arc length has to be linear. So just see what happens if your theta, which has to be measured in radians, is 2 pi. Because if theta is equal to 2 pi, well, that means the whole circle's 2 pi r. So that's a justification there as to why L equals r theta is the arc length formula. And then we just differentiate. Because if we take the derivative of L with respect to theta, well, that's just going to be r. So multiplying through by d theta tells us dl is r d theta. So anytime you have a circular arc, you might want this substitution. Now let's verify A is 2 pi r dr for a disk. So again, what this is relating to is anything with this sort of circular symmetry, where you want to think about the area in a small sort of ring, sort of like this. Because again, we can build a disk by putting all these little circles together. So I might actually make a better looking circle than that. If you think about something approximately circular like this, we're really interested in the area enclosed in this little extra addition because we're looking at how much extra area do you get by adding another ring to this situation. So there's two ways of going about this. The first way is sort of deriving this, which is what we're going to do. So my change in my area, dA, is going to be equal to the length of this ring times its thickness. Now the length, well, that's just going to be the circumference, 2 pi r. And then my thickness, we're assuming that this ring is a very small thickness, dr. So it's a 2 pi r length extended for a distance of dr. So that's why this dA can be written as 2 pi r dr. But for a more like shortcut way, we could of course like relate this to the previous example where we know that the area of a circle is just pi r squared. So this means that dA with respect to dr is 2 pi r. So multiplying both sides by dr just tells us dA is 2 pi r dr. So again, the differentiation approach works there. So we can do the same argument with the spherical shell to show that this is a spherical shell area and this is its thickness. But maybe let's just go to the volume of a sphere formula for this one. Volume of a sphere is 4/3 pi r cubed. So dV with respect to r is just going to be, well, multiplied by that 3 when you bring it down for the power rule, so it eliminates the 3 in the bottom, so you get a 4 pi r squared, and then multiplying by dr does get us the expected result. And then lastly, we'll do the cylinder. So we might want to visualize, because the volume of a cylinder formula is less known than the one for the sphere, even though the cylinder one, conceptually, I think is easier to come up with. So for the volume of a cylinder, for any symmetric shape, we know that it can just be written as the area times the thickness. And if I have a cylinder, well, its cross-sectional area can be just that circular cap of pi r squared. And its thickness, well, it's going to be extended all the way down that tube, which is L. So that's why we get the volume of a cylinder is just pi r squared L, where L is like the barrel length, and r is, of course, the radius. So we can see that dV dr is just going to be 2 pi r L. So dV is 2 pi r L dr. All of these substitutions will be helpful for us in the future, even if not just in this section. Because whenever we break apart a shape, it's helpful to replace its volume, area, or length element with something that relates to the geometry. So if you ever have a sphere, you probably want to replace its dV with 4 pi r squared dr, for example. So now let's use some charge densities to get some total charges. A circular arc of radius r holds linear charge density lambda. Well, this is constant, so no calculus is required. So we just know that the total charge is just going to be lambda times the total length. And this is a circular arc. So once again, we can give ourselves a little circular arc. So we just want the length of this circle. And the length of a circle, of course, that's just its circumference. So we just get lambda times 2 pi r. A charged rod that on 0 to L has a varying charge density. And I didn't even state what it is because we'll get all these different charge density formulas. So we're just going to do it in general. So a rod is set up like this. It has a varying charge density. Well, we know that a tiny charge segment on the rod, you can find how much charge is on it by taking the charge density at that location and multiplying by the change in length on the rod. And in this case, our little change in length, well, that's just horizontal. So it's going to be a dl is equal to dx anyway. So we can just say that my total charge is just going to be the sum of all the little charges. And I start chopping the rod at x equals 0, and I go all the way until x equals L, and I just add all of my length times thickness pieces to get my total charge. A hollow sphere of radius r holds charge density sigma. Well, once again, anytime it's not varying, we don't need to use calculus. So surface charge, that's an area related quantity. So we know that my total charge is just going to be my charge per area times the total area of this object. And if this is a sphere, the area of a sphere is just 4 pi r squared. This substitution is very common for conducting spheres, right? Because we know that all charges go on the surface of a conductor. So anytime you have a spherical setup and it's a conductor, you'll see sigma used in that case. Then we have an insulating sphere. So this is a case where you can actually have charge that's inside the sphere, and we're given some sort of density function. So here's where we have to be careful, and a lot of people make mistakes for this. So if we're trying to find the total charge in the sphere, the charge density varies with radius. So we're going to be chopping the sphere up into all these little spheres and finding the area, the charges in each of them, and we keep adding and adding and adding by building this sphere out of shells. So we know that a tiny amount of charge can be found by taking the density at a given location and multiplying that by the volume change. But we have to remember that this varies with r. So we have to figure out how the volume of our enclosing sphere changes with r. And of course, if we have a little spherical shell, the extra volume we get from expanding the shell is just the area of the shell, 4 pi r squared times dr. And again, another way we visualize this in the previous problem is saying that v is equal to 4/3 pi r cubed. So that means dv is equal to 4 pi r squared dr. Just so you can see that. So if you write your v and just take a derivative of it, that tells you what to replace the volume element with. So now we just go ahead and integrate. So our total q is just going to be the integral of all the little q's. And my smallest radius would be 0. My biggest radius would be the big radius of the entire sphere. And I integrate the quantity rho times 4 pi r squared dr. So you can't pull anything out of the integral here except the 4 pi. So that little r squared is not a constant, so it can't come outside. But the 4 pi can. So now we'll go to the actual meat of the section, and that is finding fields and potentials by chopping objects up. So the first step is to split objects into many dq segments. So if it's a rod, we have these little segments here. And after you have the segment, you want to find how much charge is on each segment. So it's either lambda times length, or sigma times area, or rho times volume. Then you want to figure out the distance to each segment. So you define some variable if it's not already there, and you figure out the distance to the segment. And you also want to figure out what your range is. I usually like to just use what's the smallest distance to the segment and what's the largest distance to a segment. So for example, if I'm near this charged rod, the closest to segment would be this distance, and the farthest segment would be this distance plus the entire rod. Then you build your integral and evaluate. So you plug in for your DQ and your R, and you evaluate. So for potential, it's pretty straightforward because all you got to do is find DQ and R. And sometimes you don't even need to find DQ because a lot of stuff will factor out. But for the E field, it can be a bit more complicated because E field is a vector. So if there's no vector things happening, meaning all the fields add, you can just plug into the E field formula and it works the same way. But if you're in a case that needs components, like this arc of charge, you have to tack on a sine theta or a cosine theta to all your terms. Because if we look at what a arc of charge would do, there's all these little wedges of charges. All of these wedges are going to push a field away using the sources and sink rule. And notice by symmetry, every horizontal piece gets canceled by a horizontal piece of another part of the arc. So when building this arc integral, you'd have to tack on a sine or cosine term to extract only the vertical pieces. Everything else works the same way, where you want to figure out your DQ in terms of the given quantities, and then you build your integral. But for E field, there is also an approach that works in cases where you are at a variable position, where you can place your point of interest at different spots. And if you have something like that, you can actually just do the potential first, which doesn't require vectors, then take a derivative by using the field potential relationship and get it done that way. So that works too. And a lot of times, just finding the potential first and differentiating can just be easier. So let's do this example that was presented above of field and potential from just a charged rod. So we have a positive charge uniformly distributed across a rod. We want the field at distances A away from the end of the rod. So first, we just want the linear charge density. So linear charge density, that's called lambda. And lambda, that's just charge per length. And pretty straightforward, we just have a charge Q and a length L. So anytime we need a lambda, we know it's Q per L. Using integral calculus, derive an expression for the potential distance x from the right end of a rod, taking the potential to be 0 far away. So I think we should call this x. So we know that the integral we're building is k times the integral of dq over r. So we need an expression for dq, and we need an expression for r. So we already said that dq, since this is a rod, we're going to use linear charge density. And our lambda, we said, was q over L. And dl is just going to be dx. Because if we have these distances x, we know that our little dq in the segment dq is just going to be lambda times dx. I always think it's a good idea to just label on your figure where that comes from. And now we'll actually just look at our R values we range over. So it might not be the best practice to just rename some variables with some things you've already used, but I think it's fine, where we just call x. So we're given in this problem that the distance to the rod is x. Let's just replace this. We're going to call this x. So we're looking for all of the different segment distances I need to take into account. Because notice that this part isn't changing because the q over L is constant, the dx is constant. So all we have to deal with is figuring out the range of values we're going over. So if I look at my first segment length, the closest I could possibly get to the rod, well, that's just going to be x. Because even at its farthest, I'm still not on the rod. So this is my minimum distance I'm looking for right here. Like my minimum segment distance is x away from one end of the rod. And then my farthest distance is not only the x I started from, but it's also the entire rod, because all the way over here. So that's an L added on to my original x. And now we got to evaluate. So Q over L is constant, so we get KQ over L times the integral from x to x plus L of 1 over x dx. And this is a known integral. This is a special case because the power rule breaks down because you'd get x to the 0 over 0. So this is a special case, right? 1 over x, that's natural log. So you get kq over L times ln of x. Yes, I know there's an absolute value, but it does not matter because we're dealing with positive quantities here. So now we just evaluate our integral. So top limit minus bottom limit. And you might want to leave it like this. It might help to leave it like this when we do a derivative later, but we can actually use a log property to turn subtraction into division, because log of b minus log of a is log of b minus a, or sorry, b over a. So we can just combine these logs using division and get an answer this way. And if we really wanted to do some simplifying, we could even write it a step further and distribute that x to get it in this form. But I honestly think stopping at this form in blue might be more informative for us. So that's the potential. Now, of course, we're doing electric field. So the E field integral is k times the sum of it's not r, but r squared. And we have an r hat, meaning this is a vector, so tack on a sine or cosine if we need it. And if we look up above, every piece of the wire or the line of charge here, it's just going to be a rightward E field, a rightward E field, a rightward E field, each of these pieces down the wire, because it's entirely horizontal. So there's no vector ideas that have to go on here. So I don't have to put a component maker. So sometimes we'll call this the component maker if you have to tack on a sine or cosine. So this means we can just plug in everything we had originally. We said dq was lambda times dx. And then we said x was the distance to one of the segments. So x was our minimum distance and x plus L was our maximum distance. And that was it. So we had no component maker or anything to deal with in that problem. So we get kq over L times the quantity times the integral from x. I don't know why I'm x to x plus L of 1 over x squared times dx. And this is one we can just do the power rule for, so you might want to rewrite it. As the integral of x to the minus 2 dx for that power rule. So again, that means that we can just, we get x to the negative 1 over negative 1, which is the same thing as minus 1 over x. And then we plug in our limits. So we'd get kq over L. I'm pulling out the negative first. So you get 1 over x plus L minus 1 over x. And then since I typically like to make this a positive quantity out in front that I can look at, we can flip the sign by bringing the negative back in and get kq over L times the quantity 1 over x minus 1 over x plus L. And this is more clear to me that this is a positive quantity because I can see I have a positive number in front and I am subtracting a fraction with a big denominator away from a fraction with a smaller denominator. Again, all I did in the algebra simplifying is I just distributed this back in. So now we can verify that if I didn't want to use components, which I didn't have to anyway, but if I didn't want to use the E field definition, I could instead just use the potential, because we know that E is the derivative of the potential. And our potential, as found in the previous part, was kq over L times, kind of looking back here, So I don't have to do any derivative rules. I'm just going to look at this form, ln of x plus L minus ln of x. And of course, the negative and the kq over L, that doesn't affect the derivative. So those are constants that can be brought out in front. And I'm just taking the derivative of ln of x plus L minus ln of x. And this gets us negative kq over L times the quantity. Derivative of ln is 1 over the stuff times the derivative of the stuff, meaning the chain rule. There's no chain rule thing here, so we just get that. And doing the same trick where we just move that minus inside to change the subtraction order, we get kq over L times the quantity 1 over x minus 1 over x plus L, which is exactly the expected E field. So again, we could have just taken a derivative to get the same result. So notice those do match. So if you already found the potential, which is often a lot easier, you can take a derivative to get the field. And now we'll verify that far, far away, the far field approximation is valid. And that means if we go far away from this rod, it should look like a point charge. Because yes, right here, it's going to look like a rod at this observation point. But if I zoom way, way out, it should just look like a chunk of charge. So let's look at that. So when we say the far field approximation, we usually just say look at the E field. So E is kq over L times the quantity 1 over x minus 1 over x plus L. And we know that this is going to look like a point charge if it works. So if this works, we're looking for like an x squared. So maybe getting a common denominator is a good first step here. So by getting a common denominator, that means the x plus L is needed from the first term, and x is needed for the second term. So that's our common denominator. So we see that the x actually does cancel. So we get kq over L times L over x times x plus L. And that's going to cancel out. That's going to cancel out the L. So we get kq over x times x plus L. So why this is helpful is because now we're going to use the large distance approximation. So if x is much, much larger than L, that means that the x is going to dominate the L. So adding this L is not really going to affect this value of x, because if x is 1,000,000 and L is 1, 1,000,001 and 1,000,000 are basically the same number. So we say that x plus L is approximately just going to be x in that case. And if we can do that, replacing x plus L with just x, we get E is approximately kq over x squared, which does work, right? Because this is a point charge. This is a point charge field. All right, next one. We have a rod with changing charge density. So this is just a rod that's set up on the axis here, and we're given a function that is determining its charge density. So if A is positive, this would mean that this part is positively charged, then it's more positively charged, and more positively charged, and even more positively charged. So all of these rod contributions aren't doing the same thing to that field. So we just want the net field strength at the origin. So once again, we just start, we want an E field. So we integrate a dq over r squared r hat. And we got to get rid of dq, we got to get rid of r, and we got to make a component extractor if needed. So dq, this is still a rod, so lambda dx is the one we're going to want. And lambda was given to be ax cubed. And we're slicing along the x-axis, so dx gives us our little charge segments. And now if we go in and try to build our integral, we see that for our distances, we're just going to call our distance x again. And the closest distance we can be to a segment is going to be x1, and the farthest distance we can be from a segment is x2. So our closest segment is at x1, our farthest segment is at x2, and there's no components needed for this problem because everything's horizontal. So I can pull out the a, and then x cubed and x squared, well, that just leaves an x in the numerator. And then this antiderivative is just x squared over 2, evaluated from x1 to x2. So we would just get ka over 2 times x2 squared minus x1 squared. And that's our net E field at the origin. If you did the potential, it would be the same story, except you'd get a different power because you'd be dividing by an x instead of x squared. So you'd get the cubic variation of this. All right, this one, we got the arc. So now we have the arc of charge. So for the arc, we're given that this is a negatively charged arc and it has lambda given to us already, so that's nice. And because we know we're going to need it, we know that dq is going to be lambda times dl. And here's a case where we can't just use dx, because dx, that's like a horizontal wedge. And dy, that would be a vertical wedge. So we actually need to substitute away using arc length, because we know that L is equal to r theta for an arc segment. So we know that dl is actually r d theta. So we'll actually replace L with r d theta in this case, if we need to do that. So we'll show two ways of doing this. So using integral calculus, derive an expression for the electric potential at the center of the arc, assuming v equals 0 far away. So of course we'll build our integral like we always do. V is the integral of k dq over r with no vectors at all. And we said in this case dq was lambda times dl, which is lambda times r d theta. And then our distance, well, here's a case where distance is the same, right? Every single segment I draw is a distance r from the center of the arc. That's what it means to be on a circle. So all of these distances are r. So now we get something interesting happens, because the r's cancel out and lambda comes in front. So I get k lambda times the integral of just d theta. So now we can go back up here and look at theta. It has to be measured in radians as part of the arc length formula. And if we just look at how much angle we sweep out, first, our smallest circular arc is just going to be this segment right here, which is 0 in radians, right? And then if I sweep all the way up here, this angle right here makes pi over 2, but then I continue sweeping all the way over here, which makes pi. So this is a full half circle. So my angles go from 0 to pi. So we get k times lambda times pi as my potential. There is an alternate way of doing this, and it uses the scalar nature of potential. Oh, and I should make this negative. Let's make this negative, because this charge density was given to us as negative. So another way of doing this is using the fact that potential is a scalar, and all of these points are the same distance away. So it should be the case that V should just be kq over r, because this should behave like a point charge potential. because all of my contribution segments are distance r away. So we just got to expand out q. So what is q? Well, q is going to be just lambda times the length of the segment. So it's going to be negative lambda times how long is this arc? Well, this arc, it's a half circle. So it's not 2 pi r, which is the circumference. It's pi r. And we see that it is consistent. We get the same answer. So we could have used a quick shortcut and gotten the same answer with a lot less, well, no calculus at all, I guess, for the blue version of this, where we just said take it to be kq over r for a point charge. Works out. Suppose a point particle with mass m and charge q, sorry, this should be charge negative q, I didn't change this, is placed at the center of the arc and released from rest. Derive an expression for the speed of the particle upon reaching a distance very far away. So making this a negative charge. So if I place a negative charge at the center of the arc, it's of course going to get repelled and launched very far away. And of course, we can just use potential, right? Because anytime we want speed, we use delta k is minus delta u, which is minus q delta v. And in this case, our charge, we're going to call that negative q. And our delta v, well, if I go very, very far away, that means my potential 0 over there. And my potential at the center of the arc, we determined was, that's going to be minus k lambda pi. So our delta v, because this is v of infinity, and this is v at the center. So that's just going to be kq lambda pi. Notice it's positive, showing that we are speeding up. So that allows us to just write our delta k, which is the change in kinetic. So our two kinetic terms is going to be equal to the amount of kinetic energy gained. Multiply both sides by 2, because we said it's released from rest. So we get mvf squared is 2kq lambda pi. So we can divide everybody by m to get v squared is equal to 2kq lambda pi divided by m, or vf is just the square root of that entire expression. So quite nasty looking. And we can show that this looks unit-wise, even though it looks kind of odd, it still is that form of the q delta v over m by expanding out sort of what this lambda is. All right, now we have the more grueling task for the arc, and it's not the potential, it's actually the field. Because here's a case where we do have to take components into account. Because if we actually look at our arc of charge here, if you look at, for example, these 2 points on the arc, this is negative, so it's going to be a sink. This only affects how I draw my picture. It doesn't actually affect the answer at all. But we see that if we draw any 2 arcs that are symmetric about this sort of center point, we see that they're going to cancel horizontally. So there's some symmetry here about this center point of the arc. So what that means is that when we do our E-field expression, we actually only want the vertical parts. So we do know that E is the sum of all of the k dq over r squareds with their components accounted for. So once again, there is this trade-off here, because once again, the easy part for the arc is that all of the distances are r. There's no variation in segment distance. But what there is a change in is we're going to have to deal with a component. So we can also replace dq with our substitution earlier that we said a tiny amount of charge on the arc is just the density times the length of the arc. And this is our tiny arc length for dl. So we get lambda times r d theta. And then we have to deal with components. So we do actually have to factor in a sine or a cosine in this case. And in this problem, well, we want the vertical part. So if we always define this polar angle as like the natural pre-calc angle here, that's going to be a sine theta because we want the vertical part. So now we can do some simplifying because we can get one of the r's divides out and the other one can come out in front. So we get k lambda over r. And then we're integrating sine theta d theta. And we argued in the last part that if we define this theta this way, the smallest my theta could be is 0, because at 0 radians, it points to the right side of the arc. So then to point at the left side of the arc, well, notice it makes an entire half revolution. So that would be when theta is pi. So now we integrate that to get k lambda over r. Antiderivative of sine is negative cosine. So we'll factor that out. So negative k lambda over r. And we're just doing the magnitude in this case. Oh, we want the magnitude and the direction, but we'll do the magnitude first. So we'll say this is going to be the magnitude first. So we get cosine of pi minus cosine of 0. Cosine of pi is negative 1. Cosine of 0 is 1. So we get negative k lambda over r times negative 2, which is just going to be 2 k lambda over r. Once again, I know this doesn't quite look like the units of E field, but if we use the fact that lambda is q over pi r, if we use that fact, you see that we do get 2kq over pi r squared, so we get some sort of kq over r squared. And we wanted the direction also. So realize that all of these components, since these are all sinks because it's a negative charge, it's going to be some sort of upwards pull that doesn't get canceled and a left-right pull that does get canceled. So this field is upwards. And we can't use the calculus relationship to easily get this E field because this field expression and symmetry isn't valid everywhere. There's only perfect cancellation at the center of the arc. So this is the exception to like take a derivative because there isn't really a coordinate that we can take a derivative of in this potential formula because it was specific to one special point. It wasn't like the rod where we could pick anywhere along this collinear with the rod. We had to specifically be at the center of this arc for this derivation to work. So suppose instead we replace the arc with a full circle, which has the same radius and same charge density. It is a negative charge density. What's going to happen to the potential? Well, potential is linear. It's a scalar, right? So potential is a scalar. So this entire thing represented the potential for the charge distribution we originally had. So we originally just had this half arc. So for the potential at the center of the circle, well, all I did is I just gave another arc of the same parameters that's directly below it. So my new potential is just going to be 2 times the old potential. Because it's the same distance, I just literally doubled the amount of charge that can be seen a distance r away. So instead of negative k lambda pi, we're going to get negative 2 k lambda pi. This potential is a scalar. Now, what doesn't work that way is the E field. Because if we look at the E fields, Now, instead of everybody having a left and right neighbor that will cancel, we also get an up and down neighbor that will cancel. So we can also break the arc into pieces that will cancel in all directions. So the E field at the center is just going to be 0 by symmetry. Because if there's negative charge all around you in the circle and everybody is a sink, well, you're not going to get pulled anywhere on average. Because if we think about it, no matter what point I draw on this arc, like let's say I looked at this segment, if I got pulled this way from this segment, well, there's an equal segment down here that's going to pull me the exact same way and cancel me out. So any point I could pick in the full arc, there's another point on the arc that is exactly 180 degrees opposite pulling me. So E equals 0 in that case. Now we have a quick ranking to do. So we have they have the same equal negative linear charge density. So this is still basically what we have going on here. It's our arc again, where we have a quarter circle, a half circle, 3/4 circle, and a full circle. We want to rank the potential from most negative to most positive. And then we want to rank the E field at the center from least to greatest magnitude. So first of all, for the potential, this one is way easier because for the potential, you have some unit of negative charge. You would have 2 units of negative charge. You would have 3 units of negative charge. And you would have 4 units of negative charge. So since potential is a scalar, it's just going to be D is the most negative. D is the most negative because it has 4 units of negative charge. C has 3 units of negative charge. B has 2 units, and A has 1. So, because we know that V is a scalar. So, for our justification, we know that V is a scalar. And since we have the same distance for all segments, we know that we're simply just ranking the charge. But then for the E field, we know that E field is, of course, a vector. So E is a vector. So let's think about this here. So for my first one, I have a field like this. Because we know that it's going to get mostly pulled sort of in that direction, kind of on average. But in B, we have that arc and its neighbor to the left. So we know that these are actually going to add to get me a net field that's going to be upwards. So it's going to get stronger from A to B with these vertical components are adding up. Then for C, we know that we're always going to get pulled towards the center of these arcs. But notice that the addition of the new arc actually cancels the first original one. So C actually gets canceled out slightly. And then, for the same argument, D gets canceled out entirely. So we see that our weakest field is actually case D because it gets pulled equally in all directions. Then we have cases A and C tie because they have one full arc. And then B, we have vector addition that causes it to be the greatest. So B is the greatest, and D is the least, with A and C tying. So we know that E is a vector. So we know that the field begins to cancel after a semicircle is created, because then you start getting symmetric segments. So the semicircle is your strongest possible arc, and you can actually work this out analytically if you're not totally sold on this fact that this, even though there is some slight cancellation happening, is still going to be longer than this. If you do this in general and integrate our previous result from like negative phi to positive phi, you'll see that this works out. You get the greatest field when it is a semicircle. Okay. For our penultimate charge distribution derivation, we have a ring. So this is a charged loop, and I'm looking above the axis. So think about this full case, except I am looking down on it from above. So I'm at a point above the center of this loop. So, of course, we know how this is going to work at this point. We define some distances, we define some charge densities, and we just get going. So, first of all, this ring is in the xy plane, and z is on the z-axis. So we know that x and y are perpendicular to z, so we actually get a right angle here. And anytime we have a right-angled triangle, it's probably going to be useful to get some Pythagorean distances and some lengths in here. So this length is, of course, the Pythagorean distance, z squared plus r squared. I like it the other way. R squared plus z squared. I know it makes zero difference. And we might want to define this polar angle theta, because we like to do some things with angles. So now, first of all, potential. So what is potential? Well, potential is the sum of all of the k dq over r's. We'll show something nice that happens here. Sometimes it might help just to do dq last, because if there's some nice symmetry, we see that we don't have to go through the effort of chopping up our ring. So, because in this case, dq is dq still. But what is r? Well, r is that distance to a segment on the ring, which is r squared plus z squared under a square root. So we're going to use something we learned from the arc example to not instantly skip to breaking apart dq. We totally could, and you will totally get a right answer by saying dq is lambda dl, which is going to be some form of lambda q over 2 pi r times blah, blah, blah. You could do this. It will work. But we'll show that patience kind of works out here. Because if we looked at the arc example, we said this basically simplified to a kq over r if all of our distances were the same. And this ring is actually the same case, where it's just a kq over r. Because notice that what I'm doing is I'm basically just sweeping around the arc at this angle. Everything stays constant throughout this process because r stays the same to each segment because it's on a circle by definition, and z stays the same because my observation point hasn't moved. So actually everything here can be factored out of the integral. So I get k over square root of r squared plus z squared, and then I'm just integrating all of the little dq's. And we're actually given that the total charge of the ring is q. So this is kq over the distance. So this is actually of the form kq over r. It's just our representative r in this case is the Pythagorean distance to the ring. And now we'll see something similar happens with the E field, even though the E field has a nastier integral. So using integrals, find the E field as a function of z. So we know that E is going to be k times the integral of dq over r squared, and then we have to have a component maker. So here's a case where we actually want to figure out what's going to happen with the components. So in this case, if we draw our ring again and we look at a point above the ring here, here's our observation point. Let's consider like this purple segment. This purple segment is going to generate a field that way. And if I go directly to the other side of the ring, this blue point, that's going to direct a field this way. So we actually just want the vertical component again, because by symmetry, there shouldn't be anything going on X and Y by symmetry because the loop is symmetric about the origin. So it makes sense that the only component we want is actually the Z component. And you could do the same argument on the other sides of the loop, and it works the same way, where you get a contribution that's always going to be this sort of up through the axis of the ring, and it's just sort of rotating around in sort of a cone. So what we want from that is, well, we want this sort of Z component. So it's the component that doesn't touch theta. So R is still that Pythagorean distance, so we square the square root. And then we want sine theta, because sine theta is going to extract this opposite component, the one that points up in our diagram. What is sine theta? Well, sine theta is opposite side, which is Z, divided by hypotenuse, which is R squared over Z squared under square root. And notice none of this has varied yet, because R is the same, Z is the same, and we haven't even messed with dq yet. So I can have a k in front, I can have a z in front, and I can pull out the r squared plus z squared to the 2 halves times the r squared plus z squared to the 1 half. Gets us that 3 halves power. And then the only thing that's left in the integral is dq. So it's the same idea. I just add up all the q's and I get q back. So I get kqz over r squared plus z squared to the 3 halves. And this should kind of look familiar. This is almost that problem we did with 2 charges symmetrically placed along the axis. And it's not really a coincidence, because it's that same idea of, you can actually do this problem by, instead of pretending it's a ring, you could have just broken the ring into a q over 2 here and a q over 2 here. You could have condensed all of the charges there. There's no reason telling you should have done that, but it does work. Now we can verify that we could, instead of dealing with the sine theta stuff, we could have just used the potential function. So we said that V was kq over r, where r is that Pythagorean distance. Because I didn't have to even do any integrals here, because it's just kq over r, because all my charge was that distance away. So E in the z direction is just the negative downhill slope in the z direction. So we can pull out the negative and the k and the q. This is very similar to the problem we did with the 2 charges on the axis. And again, a square root in the denominator is a negative 1/2 power. So we get negative kq times, bring down the negative 1/2, decrease negative 1/2 by 1, multiply using the chain rule to get that inside derivative, and we do get the exact expected result, because the negatives cancel, the 2 and the half cancel, so we pick up a z on top, and we get our 3 halves power. So this is a problem where a lot of students elect to just do it using potential, because potential is extremely simple from this problem. We did bring out an integral to start, but you didn't have to, because you totally could have just seen that the potential of this ring is just kq over r, where r is that Pythagorean distance. And if you knew that, you could have instantly just taken a derivative to get us that. And we'll make sure that this works out to both results when z equals 0. So z equals 0, again, that means that I'm not on the axis, I'm at the center of the ring. So this is, I'm surrounded by a charge q at the center of the ring. So for v, when v, we said v was equal to kq over the square root of r squared plus z squared. So when v is 0, when z is 0, that's kq over the square root of r squared plus 0. And that's kq over r, which is definitely what we expect, because you have a charge q surrounding you a distance r. That makes sense. And then we'll see that E works the same way, because we said that E was equal to KQZ divided by R squared plus Z squared to the 3/2. And this is an even easier check. So if I'm at the center of a ring, or center of a circle, I'm getting pushed equally in all directions, so it better be 0. So we see that when Z equals 0, the E field, well, that's just going to be K times Q times 0 divided by some stuff I don't necessarily care about. I just am checking it's not like an indeterminate form or anything. But I get 0 on top and not 0 on the bottom, so I can safely assume the E field is 0. So this is as expected, right? Because we're just still a point charge surrounded, still like a point charge potential, because I'm just surrounded by Q, a distance r away. But the E field should be 0 because there's not going to be a direction of net pull or push. So this is as expected. I'll put my little check mark saying that we went through this. And believe it or not, we are not done. We have one last derivation to do. And this is the rod, except this sort of uses everything we've done so far. So this is the rod, but not at a point on the rod, not collinear with it, but instead along its bisector. So we're just going to evaluate two integrals here, or just write them. If you hate yourself, you can evaluate them. Like, feel free. But so we're going to look at a point above this wire here. So first of all, why do we pick the bisector? Well, if we pick the bisector, this allows us to utilize symmetry, because right at the bisector, our sinks are going to cancel horizontally, leaving just a vertical field. But potential, let's just start with that. So we know that, of course, potential is the sum of all of the k dq over r's. So that r is just going to represent this distance right here. And let's just call this distance, let's just call this distance x on the horizontal. So we actually want this a distance y, is what we said in the problem, even though I called it b up here. So let's call this x. Again, when we're making the segments, you can make up an integration variable. So x represents how far away this piece of the rod is. And that means my total distance is going to be the Pythagorean distance. And this is, of course, a right angle. But now we just integrate. Oh, and we also know that since this is a rod and we have linear charge density lambda, we can just write dq is lambda dx. Nothing crazy there. You could even do the variable version of this, which is kind of nasty. So dq is just lambda dx, and r is just that Pythagorean distance, x squared plus y squared. And now we have to deal with our integration limits. So if we think about it, the thing that we're looking at are segments horizontally. So we're looking at what is the smallest x, or like what are my extremes basically. So one extreme would be my segment all the way over here. And if I'm looking all the way over here, I am half a rod to the left of the midpoint. So that's negative L over 2. And if I check on my other extreme, that's all the way over here. Well, that's L over 2 to the right of the midpoint. So this gets you this L over 2. And that's actually where we stop. I don't feel like factoring anything out from there. I think that's totally fine to just leave it like that. You could definitely do some simplifying. Like, notice this integral has that even symmetry. So we could have just summed up all the contributions from half the rod, then doubled it. So 2 times the integral from just 0 to L over 2. That works. Again, just make sure when you're sweeping with your integration variable, you're getting all of these possible slices. So another way of doing it, it's just how we've been doing it from the start. Look at this extreme. This slice is L over 2 to the left. This slice is my other extreme, L over 2 to the right. Now let's deal with the field. So the field, we've already done a lot of the heavy lifting already in defining our picture and all that. We do know that E is the integral of all of the kdq over r squareds and maybe a component maker. And do we need a component maker? Well, yeah, we said we did in this problem because these segments are going to be producing fields at the bisector that cancel each other horizontally. So yet again, I think this is the third time today that when we need a component maker, it's actually it's actually sine of this polar angle theta. So we can actually reuse a lot of the old work. We're still slicing from L over 2 to the left to L over 2 to the right. dq is still lambda dx. R is still that Pythagorean distance, x squared plus y squared under square root. And R is actually just sine theta. So we can do some simplifying again, because sine theta is opposite, which is y, divided by the hypotenuse, which is that Pythagorean distance, r. So we see with a lot of these integrals, we get that 3/2 power again, because we're dividing by another factor of that hypotenuse, right? Because sine theta, that's the opposite, because we want that vertical part, which is not touching theta. So this simplifies to k times the integral from negative L over 2 to L over 2 of lambda y divided by x squared plus y squared all to the 3/2 times dx. And we could factor out the lambda and the y, like we could have done with the lambda in the previous problem. Yeah, again, this is not fun to try to do, because this is an integral with respect to x. So a u sub isn't going to help us here. This is actually a trig sub problem. If you want to actually try it, you'd have to do the unconventional substitution if you haven't seen trig sub before. The trick is to pick x equal to y times tan theta is the integration sub that works, and then use a bunch of identities. Could be satisfying to do it on your own, especially this last part. So one thing that we'll like in this class is we don't like this finite wire, because the field is just nasty in a lot of parts. But if we consider this rod to be really, really long, it makes our integral actually converge to something nice. And we get a nice symmetric field at all points, not just the bisector if our wire is really long. So I have given us this magical fact that you could verify with Wolfram Alpha, or if you feel like doing a half page of trig sub, you can prove this result to yourself. That if we have a very, very long wire, this is a formula we're going to derive later. Let's show that this works using this integral identity I presented us. So we actually said that E could be written as this. This was what we came up with in the previous part. So we can say if L approaches infinity, which is what is an infinite wire or a really, really long rod of charge or line of charge, all of these mean the same things. This is going to mean that our E field is going to be, we can pull out the K, we can pull out the lambda, we can pull out the Y, And if L is an infinite, we can just replace the bounds of our integral, just infinity. And now we have a simpler looking integrand, even though this is not easy to evaluate. But it actually is easy to evaluate because I told you exactly what it evaluates to. So if you look in an integral table, you would see that this works out to 2 divided by y squared in this case. So E is going to be k times lambda times y times 2 divided by a squared. Well, where a is actually y in this case. So we get 2k lambda divided by y as our field from a long infinite rod of charge. But we actually wanted to show this in terms of epsilon 0, which is usually the case for E fields. So using the fact that k is defined as 1 over 4 pi epsilon naught, we can show that our E field is equal to 2 times 1 over 4 pi epsilon naught times lambda divided by y. So we see that instead of 2 over 4, that's a half. So we just end up getting lambda over 2 pi epsilon naught y. And an interesting result from this, now that we can see all the constants, is that the E field from a long wire, or a long rod of charge, is actually linear on the denominator. Because by putting all of these charges infinitely on a line, you've removed that inverse square dependency, because you had so much charges that it makes up for it with a power that it only falls off like 1 over r instead of 1 over r squared. So that's continuous charge distributions. So the good thing with this is that even though these are very difficult problems and the derivations are tricky, these are all the ones you have to know. And I even went beyond in some of these, but for APC specifically, you need to be able to recreate the integrals for this one. You need to be able to do the ring. You have to be able to do the ring. And then you have to be able to do the arc and the line of charge. So these are known derivations that you have to do, even though they are tricky. So just keep that in mind. It's about practicing these derivations. Like there's never going to be any difference to how you set up an integral for a long line of charge. So once you know kind of the setup, it's not too bad. But this is very math heavy and a pretty difficult section of stuff because there's just a lot of computing happening. And also, you never have to evaluate these integrals. We have tricks to do them using symmetry in the infinite case that we're going to show. We have a much better technique for finding the field from an infinite long line of charge. Yeah, so that's our continuous charge distributions. Again, the ones you got to know is the line of charge, collinear with it. So that was this one where it was a point collinear. You also need to be able to set up the bisector, and then you need the arc, usually a semicircle, or looking above an arc, which is a ring. So those are our cases you got to be able to set up. So it's really only 4 or 5 cases. And this is your first exposure to it.